All right, we are back again here with ECS 3706 econometrics, picking up from where we left last week. Yes, last week. So I promised that we're going to start on the last part in chapter 3, which is the dummy variables. So I think if you have seen the assignment number 2, I did indicate that the exam will pretty much look like what assignment number 2 is like. You see, so which is kind of a theory. It's more of a theory at this point in time. This is more of theory. So it's just about understanding the terms and explaining what you are supposed to do and doing very little calculations. Right. So just to remind you again, so that we do not lose focus, in econometrics, we are basically measuring economic variables, the relationship between economic variables. So we need to keep that in mind. And then what do we do in order to do that? Because we cannot test a whole population, we then go on to test samples. So in testing samples, we want to come up with beta coefficients, right, to estimate the relationship between 2 or more economic variables. So in order for us to estimate that, we use the OLS, ordinary least squares method, to come up with our estimated beta coefficients. So what do these estimated beta coefficients tell us? They give us an idea of what the true relationship is between those two variables. So you must remember that on the one side, you have a true relationship, and then on the other side, you have the estimated relationship in there. So you need to keep that in mind as we progress with our discussions. Right, so prior to what we're doing today, we're talking about beta coefficients. We discussed at length about beta coefficients, the constant term, as well as the gradient, right? We're discussing about that. All right, and then what are dummy variables? So dummy variables would be a variable that takes a value of 1 or 0. So it basically takes any of those two. Hence, they are normally referred to as binary variables. So binary comes from 2, right? So they either take the value of 0 or of 1. But how do they help us? So some concepts might seem impossible to include in the equation because they are inherently qualitative in nature. So a good example of such could be something like gender, right? Something like gender. So you can't have, gender is qualitative. You can't have someone progressing in gender. Let's say you can make male, okay, let's make female negative and male a positive. So you can't progress in the positive of male, neither can you progress in the negative of female. So it's either you are female or male, right? So hence, if you're going to represent that as dummy variable, then it can either take 1 or 0, right? We say maybe if you are female, it's going to be 1. Then if you are male, it's going to be 0, all right? But we'll look at that in an example shortly. So there's an illustration that they had here. So we are still on this, right, on this equation there. So you have yi on 3.5 there, you have yi is equal to beta naught. So you must remember there that beta naught becomes your constant, right? Which is your intercept concept, your intercept beta coefficient, or your intercept coefficient there. And then you then have a beta 1 x1, and then there on beta 2 d1, that's a dummy variable there. So we're saying it can either take 1 or 0. So in this illustration, let's see, as an illustration of dummy variable, suppose that yi represents the salary of the 8th high school teacher. So remember, we said we want to use these things maybe to make predictions, for instance, make predictions about a person's salary. So you know that a person who has a degree and the person who doesn't have a degree will most likely not earn the same, right? So we can decide, because it's a qualitative, it's qualitative in nature, then we can decide to make it a dummy variable. Say, okay, so if a person has a degree, or a teacher has a degree, it's going to be represented as 1. Then if they don't have a degree, it's going to be 0, right? So which means if you are going to find a person's salary, and on that D there is 1, it basically means a person with a degree is going to have to earn more, right, by some degree, right, or by some amount, right? It's going to earn a little bit more than a person that doesn't have a degree. So if you don't have a degree, then your part there where there's DI, it's going to be a 0. So you don't remember, we are predicting salary, so which means your salary is going to be less than the other one. So graphically, this will be represented in this way, right? This will be represented in this way. So salary being predicted on the y-axis, and then the x-axis, of course, is, suppose it's years of experience. Okay, if you're gonna put years of experience. So if you are gonna pick two people from the sample and one has a degree and the other doesn't have a degree, and they both have the same years of experience, then the one that has a degree is gonna earn more, so which is gonna be represented there by that D1, which is the one on top there. And then the one that doesn't have a degree is gonna be D0, so which is gonna be represented at the bottom there. So that's the effect of the dummy variable. Basically causes a shift there on that curve, right? So you must realize now that of course the gradient is gonna stay the same, right? The slopes of the curve are gonna stay the same. The only thing that's gonna differ there is the position of the graph. So one is gonna get more than the other. You see, so that's what that one is about there. So an example that we can have, the one maybe that I was talking about, male and female. There are some instances where in certain professions, if you are male, you earn a little bit more than, okay, let's not say, let me use a bad example. I'm hoping this recording stays here. Let me use a bad example. If you are here in South Africa, there are times where you feel that maybe you are doing the same job with a person who's white, but they earn a lot more than you. So if you're gonna represent that and predict a person's salary, you can't just ignore that. You need to be aware, is this person black or white? Then if he's white, you wanna put them on a higher pedestal than when the person is black. So though they have the same qualifications and the same years of experience, so that's gonna be represented there as a dummy variable right there. So on D0 there, we call that an omitted condition, right? It's an omitted condition, so which is a situation where, say, the person doesn't have that degree there. So that's what we refer to. So in as far as examinations are concerned, they'll basically ask you what is a dummy variable and how is it useful. Then you can wanna answer it by giving a straightforward definition, and then how it can affect your predictions the way we are discussing it. All right. So the rest of this you can just go through, but what's important for us is just the binary, those two there. All right. So just a reminder, a summary, since we picked this up from the middle. We first of all discussed the 6 steps typically taken in applied regression analysis for a given dependent variable. And we said what you need to do before you come to the conclusion that you have done a good job with your regression analysis, make sure to have reviewed the literature and developed a theoretical model, and then specified the model again, which is the selection of independent variables and the functional form. So we discussed all this last week. And then hypothesizing the expected signs and of the coefficients, and then went on to collect data, and then inspected the data and cleaned the data, and then estimated the evaluated the equation, and then document the results. Those are the 6 steps there. So a dummy variable takes only 1 or 0, depending on whether some condition is met. And then say, for example, an example of a dummy variable would be x is equal to 1 if a particular individual is female, 0 if an individual is male. So those are dummy variables. So obviously we are dealing with independent variables here, right? So you are talking about something that will, at the end of the day, have an effect on your y variable, the dependent variable, something that's going to affect if you're gonna be pretty much using this for a prediction, something that will have a bearing on your prediction, right? So to make it easier, think about the salary at your work. Once you win and get this degree, it's likely that your salary is gonna go up. So you and your colleague that didn't take up this degree are gonna be spaced now when it comes to your salary. You're gonna have a gap above your colleague. All right, so let's leave that one there. All right, let's leave that one there. All right, so all that there is what we're discussing previously. Now let's talk about the classical assumptions. The classical assumptions of this regression analysis. So the classical assumption must be met in order for OLS estimators to be the best available. Right? So there are certain assumptions that have to be met before we can jump to using the OLS. So OLS is ordinary least squares. What we did there on the spreadsheet, we're basically doing OLS. So again, you can achieve the same using your calculations, using your calculator, but it's going to take a lot of time, right? And it's not really examining, but it's good to know, right? So these are the classical assumptions. So classical assumption number one, the regression model is linear, is correctly specified, and has an additive error term. So you remember the error term, right? That epsilon, right? Stochastic error. And then the error term has a zero population mean. So we did see that on our first assignment, but we are going to talk about it again. Right? We're going to talk about it again. And all explanatory variables are uncorrelated with the error term. So correlation basically means things that are moving in the same direction, or things that seem to move either in the same direction or in opposite direction. So in other words, if two variables are correlated, you can easily predict that when this variable takes two steps, this one is going to take, maybe a step or two or three. So we say that they are correlated. They have, where we discuss, they have a negative or a positive relationship. So we are basically talking about the correlation there. Right. So we are saying the explanatory variables and the error term must be uncorrelated. Right. So in other words, your error term should not increase with your explanatory variables, neither should it decrease with your explanatory variables. They just have to be unrelated. So if they are unrelated, they are independent of each other, right? They are independent of each other. So if you are going to do the gradient, of course, after plotting them, it's just a straight line, right? When one variable changes, the other doesn't change. So as being uncorrelated. Then observation of the error term are uncorrelated with each other again. So in other words, from the different observations. So if you have observation 1, 2, 3, so the error term in observation 1 should be unrelated with the error term in observation 2. So I'll just remind you again of the definition of the stochastic term. So it has to be purely random, right? So if something is random, it's like if you're playing, if you have gone to the bets before, those numbers, I assume they are random. So because you chose, or because number 4 won yesterday, doesn't really affect tomorrow's outcome. It has to be random, right? Otherwise it becomes biased, right? And then the error term has a constant variance. So we mean there is no heteroscedasticity there. What a big word. But we're going to deal with that again specifically as a topic on its own. And then no explanatory variable is a perfect linear function of any other explanatory variable, right? So in other words, these variables should not be correlated, right? Explanatory variables, they should not be correlated. So remember, when we speak of correlation, explanatory variables should not be correlated with the error term. Then the observations of the error term should not be correlated with each other. Then the explanatory variables again should not be correlated with each other, right? And then the error term is normally distributed. This assumption is optional, but usually is invoked, right? We are going to see that there. Right, so on assumption number one, obviously, if we're going to do a regression analysis, we have that form yi is equal to beta naught plus beta 1 xi 1 etc, right through up until we get to the error term there. So the functionality of that, they assumes there is the regression model is linear. We are assuming a linear relationship. How do we see that? We don't have any to the powers of what except for 1. So a linear is only raised to the power of 1, right? So it becomes a linear. So the unknown is only gonna be raised to the power of 1. So that's assumption number one, right? So the assumption that the regression model is linear does not require the underlying theory to be linear, right? For example, it could be an exponential function there. So where e is the base of the natural log, so which is that ln, and it can be transformed by taking the natural log of both sides of the equation. So this one here, sometimes if you look at economic, the growth of an economy, that the economic cycle, if I were to put it, where there's a trough, there's an upswing, and it gets to a peak, then a downswing, like that. So it goes on and on and on that way. So though you can see that the underlying theory there may not be linear because it's polynomial, right? It's going up and down, it's oscillating, but you can basically assume a linear relationship if you're going to impose a logarithm on it, right? So in other words, though it's not straight, but if you look at it in terms of time, in logs of time, it's linear, right? For example, if you look at your life, if I may use the example that a typical motivational speaker would use. Your life is full of ups and downs, right? Your life is generally full of ups and downs. But if you look at yourself last year and this year, you can generally conclude that you have been improving, hopefully, right? So which means though it's not a linear function, but in logs of time, so if you're going to look at it from a distance, right, you can assume that your life is just going straight and up. So under those circumstances, then you can assume a linear relationship just by adding in ln or logarithms, natural logarithms there. So you are saying, though, if you take a closer look, it's not really linear, it's got ups and downs. But from a bigger perspective, through logs of time, if you look at like the way we analyze economic growth, that whole cycle, right? If you look at it through time, it's just going straight upward, right? It's just going straight and going upward as time. So that's an example of when it's when the underlying theory is not exactly linear, but at the end of the day, we make it linear by introducing natural logarithms. So which means under those circumstances, then we can basically use the OLS. So the other assumption again is, do not forget that there always has to be an additive error term. So go back again and revise the sources of the error term, right? What the error term is and the sources of the error term. Then you realize that there is no estimation that should come without an error term, right? There always has to be an error term because from the sample that you have collected, the points are not all gonna lie because it's a scatter diagram. The points are not all gonna lie on the line on that equation. So remember, so the difference between the estimated line and that distance between the estimated line and the different points from the sample is gonna give you the error, right? So once we are dealing with an estimated regression line, then it's gonna be the residual error, right? But here we are just gonna say the error term because it's purely theoretical here. All right, and then there you go. The error term is a zero population mean, right? As was pointed out in the previous section 1.2, econometricians add a stochastic error, which is a random. So it has to be random, right? A random error term to regression equations. What for? To account for variations in the dependent variable that is not explained by the model. Right, so this is a very important definition. So the specified value of the error term for each observation is determined purely by chance. Right, so this is going to be repeated there later on one of the other assumptions. Probability, the best way to picture this concept is to think of each observation of error term as being drawn from a random variable distribution, such as this one here, right? So assumption number 2 says that the mean of the distribution is 0. That is, when the entire population of possible values of stochastic errors term is considered, the average value of that population is going to be 0, right? So this is very important there. So we are assuming a population mean of 0. So if you think about it, there was a question there that was saying, that read on the assignment, that was specifically talking about after we ran our OLS, our regression model, which was talking about what's the total that you get after you add your residuals, right? The total was given as 0 then. The total was given as 0. So that's one important characteristic that you get there. So if it's 0, it means all possible values of your residuals lying on that side for your stochastic error. So your residual is predicting your stochastic error, by the way, right? Those residuals should predict the stochastic error. So all values that lie below 0 must be the same as all the values that lie above 0. So hence, if you total up all those amounts, it should give you a 0. Right? That's what was happening here. So just remember that what you are trying to estimate in OLS, you are basically trying to estimate true relationship or the true betas, right? You want to estimate the true betas, which basically gives you the true relationship there. So since we have a stochastic error, so once we run the regression, what we get residuals, and at the end of the day, the mean of those residuals will always be 0, or it should be 0. So the error term has a population mean of 0. So if you are going to consider the whole population, therefore, if you are going to consider the whole population, for argument's sake, you have tested the whole of South Africa, then your betas are means, by the way. Your betas should be a mean of what you've tested, right? It's the average of what you've tested. It gives you beta, right? Your estimated beta. So if you take a sample of, say, of Bloemfontein, right? You test Bloemfontein, it will give you a certain average. So that average, say your beta naught is going to be the average according to the sample there. Your beta 1 is going to be, that slope coefficient is going to give you the average based on what's given there, like the average of all the possible values of that slope. So meaning, remember, your line can basically lie anywhere, because this is it's more like a scatter diagram, right? So you can pretty much draw your line anyway, but we said your OLS gives you the average, the best. In other words, the line of best fit, which should run in the middle there, which should give you a mean. So hence your beta estimates represent the average, which is going to be, in this instance, if you're going to plot it like this in your probability as a probability distribution, then it will give you a 0 there. So once you test the whole population, therefore, instead of taking Bloemfontein, you take the whole of South Africa, and then your calculations should give you a beta. So it should give you a stochastic error of 0 there as a mean, right? That's what you should basically get there. And then all explanatory, now we're on number 3. So all explanatory variables are uncorrelated with the error term. Right, they are uncorrelated with the error term. So it is assumed that the observed values of explanatory variables are independent of the values of the error term. So remember, your explanatory variables are your x1s, x2s, x3s. So they need not to, or they should not be related with the error term. Right. So if an explanatory variable and the error term were instead correlated with each other, the OLS estimates would be likely, or would likely attribute to X some of the variations in Y that actually came from the error term, right? So that could be the possibility. So if it's positively related, for instance, then there's a likelihood that your predictions will go up. You see, it's likely that your predictions will go up. Then if unnecessarily up, then if it's negative, it's likely that your predictions are gonna go low. So some of the reasons that could explain or that could lead to this is when we have omitted a certain variable. Let's say you are dealing with trying to predict the GDP, and then you have put in, say, your interest rates, and then you've added the error term. So some of the variables that you left out there that are captured in the error term are actually gonna affect your prediction, right? They're actually gonna affect your prediction. For example, there could be a change in the fiscal policy, right? So because you don't have government spending included there in your equation or in your model, then that change in the fiscal policy is going to be captured on the error term, right? Remember, the error term captures every other movement that is not, every other variation in Y that is not caused by the X's that you've included. So which means if there's an X that you omitted, that X is going to be included in the error term, right? So which means whenever there's a change in the fiscal policy, it's going to seem like it was caused by your change in the X's. You see, so it's going to give you a wrong prediction there. It's going to give you false readings. So hence we're saying you need to look for all possible explanatory variables and make sure that they are all included there, right? So otherwise, if there's a relationship now between the error term, so how to pick that up now, particularly if you've omitted a variable, you normally see a correlation between a relationship between the error term and the error term and variables. So that's what you would see there. So we do not want it to be violated, right? That assumption. And then 4 observations of the error term are uncorrelated with each other. So this would usually happen if you're looking at a time series data, right? So if you have made a mistake, say, let's think of an example. Let's say you are starting first year, second year, third year, right? And you're doing economics. So if there is a problem with your first year economics, it's most likely going to affect second year economics, right? Then if it's not fixed again, it's going to affect third year economics. So this is an example where if the problem that we're talking about is an error term, a problem that you don't know, then it's going to affect the following year and the year after. So it becomes related, right? It becomes related. So in other words, if you made a mistake last year, then it's likely that you will make a mistake the following year. So if you failed ECS 1601, it's likely that you will fail in 1602. What's the other one? 2602. And then you'll also likely fail, say, monetary economics, something like that. So that's the assumption there. So what does the school do? They make these ones prerequisites so that you don't carry forward that error to the next period, right? So that your failure at second level should purely be by chance, right? We should not say you failed because you failed, first level or something like that. So that's an example where there are observations of the error term which are uncorrelated. So remember, when we talk about the error term, we're just saying variations that are not explained by the model, so which could be certain kind of failure, right? So if we have not picked up a person's results from the beginning of when they enrolled, then it forms part of the error term. So we need to clean the data of such things, right? And then the error term must have a constant variance, right? This one is what we are saying, that big word, heteroscedasticity, right? It comes here. It has 2 spellings, by the way, so you need to check that there. So when it has a constant variance, then it should look okay. We will see it when we're now dealing with when we're now dealing with heteroscedasticity as a topic on its own. But if you look at the diagram that's given there, you can see that as, okay, the example of assumption 5 not being met is when the variance of the error term increases as Z increases there, and we call that heteroscedasticity. So the observations are on average further from the true regression line for large values of Z than they are for small values of Z. So you can see how it spreads, right? How it begins to spread as we begin to move there. All right. So what is variance, therefore? Variance is just a measure of dispersion, right? It's just a measure of dispersion. So you're looking at how dispersed your points are from that line, right? So how they are spread. So it's a measure of spread, as they would put it in finance. All right. So that is, the observations of the error term are assumed to be drawn continually from identical distributions. For example, all right, on 4.1, right, which was the example before there. So the alternative would be for the variance of the distribution of the error term to change for each observation or range of observations. So in Fig 4.2, for example, the variance of the error term is shown to increase as the variable Z increases. So such a pattern violates classical assumption number 5. So the actual values of the error term are not directly observable, but the lack of a constant variance for the distribution of the error term causes the OLS to generate inaccurate estimates for the standard error of coefficients. All right. So just to put it plain, there must be a constant variance there. So whenever it's not constant, when it's increasing, like in that case, or sometimes it can be decreasing, then we don't want that. It's a violation there of classical assumption number 5. All right. So, and then no explanatory variables. Now we're on number 6, is a perfect linear function of the other explanatory variable. So we call that perfect collinearity. So we are going to deal with that later. So between two independent variables implies that they are really the same variable. So a good example of putting in your equation two variables that are essentially the same would be, say, if you're going to be measuring, say, trying to predict, okay, let me think what you could try, right? Trying to predict, say, the usage of fuel consumption of a certain machinery, and you wanna represent that there in the regression model. And then part of the factors that influence that, say, you put miles and kilometers. You see, so you have miles as one X variable, and then kilometers as the other X variable. So when your miles are increasing, miles and kilometers are not the same in the real sense, right? They differ, but what do? They basically measure the same thing. So which means there will be perfect collinearity between miles and kilometers. So every time your miles increase, your kilometers are gonna increase just by the same proportion, right? If you look at, again, say, degrees Celsius and your Fahrenheit, so those basically measure the same thing as well. So that's an example of you including variables that are perfectly linear or that are perfectly correlated, right? So which is perfect collinearity. So we are going to deal with that again. So let's see many instances of perfect collinearity or multi-collinearity if it's more than two independent variables that are involved are the result of the researcher not accounting for identities. So identities is what I was talking about there among the independent variables. So this problem can be corrected easily by dropping one of the perfect collinear variables from the equation. So you can remove kilometers and remain with miles, right? Remove degrees Celsius and remain with Fahrenheit, right? So these are things that basically measure the same thing. So perfect collinearity also can occur when two independent variables always sum to a third, right? Or when one of the explanatory variables doesn't change within the sample, right? With multi-collinearity, OLS, or any other estimation technique, will be unable to estimate the coefficients of the collinear variables unless there is a rounding error. So it will really be unable to do that. You can't run it there on the regression line. All right, and then the error term is normally distributed. So I think you will remember this from, where did we have that there? Right, there you go, you have that on that other assumption. So the error term is normally distributed. So although we have already assumed that observations of the error term are drawn independently from the distribution and has a zero mean, that's on assumption number 2, and there's a constant variance, and that's going to be assumption 5 there. We have said little about the shape of the distribution. So assumption number 7 states that the observations of the error term drawn from the distribution have to be normal. So in other words, they need to have that bell shape there, the one that we have. So this is how normal distributions basically look like there. This is how they basically look like. So they are asymmetrical and bell-shaped, right? Asymmetrical meaning the other side is just the same as the other side. So the mean cuts exactly in the middle there, right? So a normal distribution, so the spread there represents the variance. So if you look at distribution A, it has a bigger variance than distribution B there. So if this is what you have there, and 0 there represents the actual error term, right? 0 there represents the actual error term. So which means as you draw samples from Bloemfontein, you draw samples from Qwaqwa, you draw samples from Limpopo, your residual values are basically going to be lying within that probability distribution there. So they can lie, if the sample is big enough, it's going to lie closer to 0, right? It's going to, if you test the whole population, it will be 0, right? But if you test a large enough population, it has to be closer to the true value, which is 0 there. Right? But at the end of the day, those samples can take any of the values there within that probability distribution. So it's random, right? It's purely random. So if the variance is large, like in distribution A there, you can see that the spread is wide. You've got a wide distribution. So it means the likelihood of you picking a value that is further from the truth is increased, right? And then if the spread is low, there, like in distribution 2, there, then sorry, in distribution B, then most values that you're gonna pick or assume or estimate are gonna be close to the value there, the true value that you want. All right. So assumption of normality is not required for OLS estimation. Its major application actually is in hypothesis testing and confidence intervals, which we are going to be doing on the next session. And without the normality assumption, most of the small sample tests of that chapter are going to be invalid. So most of the tests that you conduct in statistics assume a normal distribution. So they only work, for instance, if you're going to do the T statistic and the F statistic, then you're going to use, or you're going to have to assume a normal distribution there. So with that assumption, without that assumption, sorry, you are going to be stuck. Okay. All right. So 4.2, now we deal with sample distribution of data of the estimated data. So it cannot be stressed too strongly how important it is for students to understand sample distribution. Right. So the sample distribution basically tells you about the number of options, right? Your estimate. So you go and draw a sample, right? And then of which they can be different samples, because let's say you want to estimate one thing, right? You want to estimate, say, what can you want to estimate, right? We are first getting to election time. So you want to estimate, say, the relationship between the money that is spent on campaigns and then the election results, right? You want to estimate that relationship and then come up with a model. So you can advise your political party that I think if you want to increase your votes by a certain number, you need to pump in this amount of money, right? So what you do, you then fly all the way to Bloemfontein. You have a sample of people that you interview. You collect samples, maybe even of from different political parties, the amounts that they spent in, the amounts that they spent in their campaigns, and then the election results. Then from there, you fly to Durban, you go to Cape Town, you do the same thing. So at the end of the day, you are gonna have a regression model, say for Bloemfontein, a regression model for, you can basically come up with a lot of those, right? So those estimations therefore are gonna form a probability distribution, right? Around, assuming that now the mean of that has to be the true value, right? The true values of those parameters, right? So at the end of the day, they become like a probability distribution. So if you take one from Bloemfontein, so it can either be close to the true value or far from the true value, right? Depending on a number of things, including the size of the sample, but because you have taken quite a lot of them, the small samples, then it's unlikely that it's going to be close to that. But at the end of the day, the mean of all those beta coefficients shall therefore give you the true value, should be able to give you the true value there. Right. So when we talk of a sampling distribution of your betas, then we are seeing the different betas that you are getting, say, from the different samples that we have tested there. So they are going to be giving you many betas, right? If you test another group, it gives you a certain beta. You test the other group, so in the end, you can make a sampling distribution of that, and then it should be normally distributed, and then you can predict. You can then use that to predict your true value, right? So this here, I can basically skip all that, right, to read. Then up until we get here to the properties of the mean, right? So an estimator of beta is an unbiased estimator if the sampling distribution has its expected value or its expected value being the true value of beta, right? So at the end of the day, after now you have all your betas that you've collected, then the estimated or the mean value of all those betas, if it's unbiased, then it should give you the true value of your beta, the true value of your, the actual value of your beta there. So beta, remember, we are talking about the coefficients, the slope coefficients, as well as the constant coefficient. So your unbiased estimator, therefore, should be equal to that one there, should be equal to the mean, or the expected value there should be the same. Hence, we refer to that as an unbiased estimator. So if an estimator produces betas that are not centered around the true value of beta, then the estimator is referred to as a biased estimator, right? And then these here are the properties of the variance that I was talking about. So at the end of the day, you have a true value of your beta there. And then as you collect a sample, you are basically trying to predict your true value there. And then you are going to get any values there ranging from any values there that are shown on that, that are represented by the probability distribution. So it means what that bell shape basically means at the end of the day is if you are using your OLS to estimate the values of your beta, say you have collected a big sample now, and you're using your ordinary list of squares, assuming that all things are well, then the expected value there, in other words, which is the value that you're gonna get there using your, remember we said the regression line is the expected line, right? So not the expected line, the estimated line, right? So your estimation therefore should give you, as an expected value, should give you a value that is very close to the true beta. So which is why shown there from the normal distribution, you can see that it gets bigger as it's approaching the beta value, which is the true value there. So we are assuming now that if you use your OLS, then your likelihood of picking up a value that is close to the true value is big, right? It's very large. So hence you see that it gets thicker as you approach the true estimated value there from the diagram. But of course, again, if there's a large variance there, there's a likelihood that you can pick up a wrong value. Again, it's quite big, right? And then if it's a small variance, then it's quite small, right? So it means that the likelihood of you picking up the wrong beta estimate is quite small as well. So that's the importance of variance there in that regard when it comes to the probability distributions. Right. So if our true value, suppose our true value is 1, right? So if you look at saying, let's start there on N6, right? If you start there on the graph N6 or the probability distribution N6, you will notice that because it's short and wide, it means that the variance is quite big, right? So the probability of you picking 4 there as a beta estimate is quite small, right? Because it's thin there. But jump straight to 3, you can see that the probability has increased. Now there's a bigger chance of you picking a value that's closer to 3. 2, it's even worse, you see. So you can see that there's a slight difference there between 2 and 1. So which means there's almost an equal chance of you picking 2, which is a little bit further from 1, you see. And then the range there between 1 and 2, there isn't a big change. So if you compare that with N600 there, you can see that the variance is small. So your chance of you picking, say, a value that is 3, there is no chance because it's not even included there, right? But your chance of you picking, say, 2 is very small, or a value that is much closer to 2 is very small, you see. But as you first approach 1 there, which is the true value, there's a very big chance. So meaning, whenever you run your OLS with a variance like that, there's a likelihood that you're going to arrive at a figure that is very close to the truth, which means your predictions are also going to be very close to the truth in that regard, right? So bear in mind that your OLS will basically give you any of the values that are there, right? But then we say it's unbiased when it gives you an estimated value that is the same as the one that's given. That is the true value there. All right, and then the standard error we are going to deal with there. So later again, I think in the next session. But since the standard error of the estimated coefficient, which is written like that, is the square root of the estimated variance, so it is similarly affected by the size of the sample, of course, right? So what they were showing here, by the way, these n's here are the sizes of your samples, right? So if you test 6 people there, the variance is going to be big. So there's a likelihood that your beta coefficients are not going to correspond with the true beta, right? So that likelihood is increased. But as you keep increasing the sample, then the likelihood, the standard error is reducing, right? How do we see that again? The variance is reducing, right? So up until you get to the large sample. So remember, when we're saying the larger the sample, the better the estimate, right? That's what we mean there. Okay, so let's just leave that now and conclude with the Gauss-Markov theorem and the properties of the OLS. So what you should remember about this one here, the Gauss-Markov, is blue, the issue blue, but we'll get to that now. So the Gauss-Markov theorem basically proves 2 important properties of OLS estimators. So we don't really have to prove that now, right? So given classical assumption 1 through up until assumption number 6, right, or 7, the ordinary least squares estimator for the betas is the minimum variance, right, from among the set of all linear unbiased estimators, right? So which means we are saying the OLS is the best, right? We are basically saying the OLS there is the best estimator. So what must you remember now about this? The Gauss-Markov theorem is perhaps most easily remembered by stating the OLS is blue. So the ordinary least squares is blue. So ordinary least squares is the method that we are using, right, to arrive at our estimation. So what was blue stand for? B stands for best, so which means it gives us the minimum variance, right? And then obviously linear unbiased estimator. right? So blue stands for best linear unbiased estimate, and we already spoke about unbiased there previously, right? All right, so I think let's just review that there. All right, so when we talk about them now being unbiased, right, again, we say it, then which means the expected value of your beta is beta, which is the true value of your beta. So that means that the OLS estimates of the coefficients are centered around the true population values, values of the parameters being estimated. And then their minimum variance again. So remember the distributions there. So the distribution of the coefficient estimates around the true parameter values is tightly or narrowly distributed as possible for an unbiased distribution. So in other words, it does not have a huge variance like the ones that we were describing there. So the OLS will give you the least variance there. Hence, it's ordinary list of things, right? So those variances, okay, no, let me not talk about that now. And then again, they are consistent, right? They are consistent. So as the sample size approaches infinite, the estimators converge to the true population parameters. Put differently, as the sample size gets bigger, the variance is gonna get smaller, right? And then the fourth one, right? The fourth and the last one, they are normally distributed again. So we spoke about this and why that is important. So it's important for the chapter that we are gonna deal with in our next session. All right, so the next session, we're dealing with hypothesis testing and statistical inference. So this is also there in our assignment, by the way. All right.